So, brief summary of last time. I say today I figured I'd discuss memory checking arguments and twist and shout in particular, which is some new work that that we released just a few days ago. But a brief recap of last time, we started talking about hashing-based polynomial commitment schemes. So everything we had seen before last session used elliptic curve groups in some way. So bulletproofs, Hyrax, Dory. And so hashing-based schemes are, don't have elliptic curves anywhere, which has, some pros and cons like almost anything in Snark design. Pro is post-quantum security, at least plausibly so, and fewer restrictions on what field you work over, because elliptic curves kind of demand a field that is 256 bits or up to make sure discrete logarithms are intractable to compute, and hashing-based things don't come with that limitation. But they do come with downsides, especially larger proofs. So the schemes we discussed last time have square root proof size and verifier time. This is square root in the number of coefficients of the polynomial being committed. They do have a nice fast prover. And there are hashing-based schemes known with smaller proof sizes, but a slower prover. However, even kind of the smallest known proof sizes today for hashing-based schemes are in the ballpark of like 100 kilobyte proofs, with a bunch of variation depending on how much recursion are you using to try to bash the proof size down without paying a major hit in prover time. How aggressive are you with security levels and things like that. So just, very rough ballpark, like 100 kilobyte proofs here. Whereas with elliptic curve commitment schemes, you can get proof sizes as low as, well, if you allow a trusted setup, as low as well under 1 kilobyte. So multiple orders of magnitude difference in verifier costs. Okay. And I will highlight something we discussed at the very end because it will be relevant to today. So this Binius and Frobenius stuff that we discussed briefly, and there's been other related work recently, like something called Blaze. They have this nice property that small values are very fast to commit to. So this is going to be relevant today. So for example, if you want to commit to like a polynomial, let's say with n coefficients, so size n. Okay, but all of the coefficients are known, to be in 0, 1, say. What you can do with like Binius and Frobenius and Blaze is you can split the n coefficients into n over 128 chunks of 128 bits each. Okay, pack each chunk into a single field element. So these commitment schemes work over binary fields, and you need 128, a field of size 2 to the 128 for security in all of these hashing-based commitment schemes. So there's sort of no avoiding working over at least 128-bit field if you want adequate security. And so the game here is to kind of make use of all 128 bits in the field, by packing 128, coefficients into a single field element before committing, right? And so this gives, I guess, n over 128 field elements to be committed. And so then you commit to those. Using whatever your favorite commitment scheme is, that commits to kind of big coefficients, rather than small ones that are just in 0, 1. So this packing technique, which was only really introduced about a year ago, in a sense, it's like 128 times better than what we knew how to do before. Waving my hands a little about, a bunch of work, working over, characteristic 2 to the 31 or 2 to the 64 or something. Basically what we knew how to do before would be to assign an entire 128-bit field element to each of these, n coefficients. And that's very expensive and wasteful. Now we're assigning only n over 128 field elements to represent all n coefficients. So it's sort of a factor 128 speed up compared to the very naive thing of assigning a separate field element to each coefficient. So yeah, I'll leave it there. So these are, by virtue of avoiding elliptic curves, we're able to work over fields of size just 2 to the 128. And they can have, very small characteristic like 2. And then the hashing-based schemes still have to work over a 128-bit field for security. But this packing technique introduced by Binius allows you to sort of make full use of all, the entire field, even when you're just committing to small values. So that will be relevant today. Okay, so today we're going to discuss, I guess, pretty specifically twist and shout, which are new snarks for memory checking. So I'll dive into that momentarily. Let me just see if anyone wants to ask any questions about the recap.
I have a quick question about the sort of the concept of like numbers being small. Because the example you gave, it's like if we know that the coefficients are 0 and 1, then we can do this sort of thing for savings. When you're doing this sort of like benefiting from them being small, do you need to have like a bound, like all the coefficients are below this bound in order to like get the savings?
Yeah, you do. It's like, if some of these, if every one of these coefficients like might be, say, an arbitrary field element, and then you sort of get well, how do I want to say this? Yeah, you need a bound. The verifier has to somehow know that.
It's almost like the formatting we're using to like do this, right? To do this like little compression trick, like needs to kind of know what the bound is in order to unpack.
Yes, exactly. Because what's going to happen is like the verifier ultimately cares about the unpack thing, right? So V is going to need to evaluate P of R at a random R, where P is the unpacked polynomial. So just 0, 1 coefficients, all n of them. Okay, but what the prover actually committed to is the pack thing, which is just a different polynomial. So P committed to something else. Let me call it P. I'll just call it Q. And so what these protocols do, Binius and Blaze and all of that, is there's you use the sum check protocol to relate the pack thing, like Q of R and P of R. So when the verifier says, "Hey, I need to know P of R," and the prover is like, "Hey, that's tough because I didn't commit to P, I committed to Q." What you do is you express P of R as like a big sum of evaluations of Q. You apply sum check to compute that sum, and at the end of sum check, the verifier only needs to evaluate Q at a random point. And now we're in good shape because Q is actually committed. So the verifier needs to know how the packing was done. That's the only way you're going to be able to relate P and Q. Yeah.
Cool.
And so there's nothing super special about values in 0, 1. I mean, it's nice and clean, but like if you knew in advance that all the values were between 0 and 2 to the 8 minus 1, you could do the packing for that as well. And it's just, rather than packing 128 values into one field element, they would fall to 128 over 8, what is that, 16?
Cool.
And so the benefits of the packing would still be significant, but 8 times less than the benefits when you're committing to 0 ones.
Nice.
Yeah. Okay. Other questions?
Nope.
All right. Okay. So let's talk about memory checking. So here, well, firstly, I'll say there are two variants. So one is read-only memory, and people call this the setting lookup arguments. And even here, people have studied sort of two different variations of lookup arguments, which I call the two variations index lookups and unindexed lookups. And read-only memory corresponds to index lookups. And then there's read-write memory. Okay, now lookup arguments, have sort of received the most attention thus far, which, in a sense, it's a little odd to me, I guess. Maybe it's because ZKVMs have only really become popular recently. But any computer obviously has read-write memory. That's what random access memory is on your laptop or whatever. And so if you want to build a ZKVM, it's like very obvious you need read-write memory. It's less obvious that you can make use of read-only memory. But you can make use of both. So what I think is going on is like back when people were very, very focused on SNARKs for circuit satisfiability. They weren't implementing or proving any notion of read-write memory. There was no VM being implemented. And so it's the read-only memory, the lookups that were useful for circuit satisfiability. But actually, if you want to build a ZKVM, it's sort of more obvious that read-write memory is useful, and it's more surprising that read-only memory is so useful because your laptop doesn't make use of too much read-only memory. Almost everything it does is sort of read-write memory. Okay, so how does one formulate the two variations on memory checking here? I guess let's start with the read-write memory case. So like before the memory checking even sort of begins, like the problem setup is the following. Like someone, let's say it's the prover, has already committed to let's say T address value pairs. Let's say 2T actually. So we have the writes. So write address value pairs. Okay, and reads address value pairs. And it turns out to be sort of easiest and cleanest to just assume that they alternate, right? So that it goes, let's say, I think Twist and Shout the paper does reads so read and then followed by a write, followed by a read, followed by a write, and so forth. And the techniques extend beyond this, but actually this sort of captures standard VMs very well. Like the RISC-V VM, almost every CPU cycle reads 2 registers and writes to a third register. So that really does look like read, write, kind of over and over and over again. And it's easier to talk about one read and one write. Everything works no problem if you had 2 reads and 1 write, over and over again. Okay, so what? Yeah, these are all committed, and the prover then wants to prove that it's kind of maintaining memory correctly, right? And so what that means is that every the value committed for the ith read operation that was written to that address, like I would say most recently. Sort of, maybe that's a confusing answer. It's like the memory checking argument is prepared to handle any values, any field elements. But in actual applications, the values often are not arbitrary field elements, and sort of the promise that they're not arbitrary field elements, like the memory checking argument doesn't really care that that promise is there. It was ready to handle anything, but that promise winds up being enforced by parts of the ZKVM that are just outside of the memory checking argument. Now, in terms of how the pairs are committed, typically there would actually just be like 4 different polynomials. So we'd have like one polynomial, maybe call it WA, that would be like the multilinear extension of all the write addresses. So like WA of 0 would spit out the address in the first write tuple, and WA of 0001 would spit out the address in the second write tuple, and so forth. So you'd have WA, which would spit out the write addresses. You'd have RA, which would spit out the read addresses. You'd have WV would spit out the write values, and RV would spit out the read values. And so, rather than having, so there'd be 4 polynomials that kind of take, the first 2 together specify the right address value pairs, and the second 2 polynomials specify the read address value pairs. Was that a clear enough response?
Yeah, absolutely. Thank you. That helps to follow further.
Great. Yeah. I think there are kind of more complicated questions as to how, like, let's say we know that, like, we fixed the memory size in advance. The Twist and Shout paper uses capital K to denote memory size. How do you make sure that all of the committed addresses are actually numbers between 0 and k-1 or something, so that they actually specify valid memory cells? And it turns out that that is not necessarily guaranteed by proof machinery, in the ZKVM external to the memory checking argument. I would say that is the responsibility of the memory checking argument itself, and memory checking arguments wind up handling that, and how they handle it actually differs. But as we discussed Twist and Shout today, Twist and Shout is very explicit that Twist and Shout is making sure that all the addresses, the committed addresses, are valid memory addresses. That no one's trying to like write to a cell that doesn't exist or something like that. Okay. Other questions?
Open minute chat.
Great. Okay. So in the read-only case, there are no writes, and so in the read-only case, like the contents of memory are like fixed in advance. Now, how they're fixed can vary. In some cases, like, let me give you 2 examples. One example would be like something that arises often in range checking, or doing byte decompositions. You have this table where the memory cell I stores field element I. Okay, so here, it's like the table, has some size, even if that size is really big, like the verifier still knows what the table is, like what the contents of every cell in the table is, and does not have to run in time linear in the table size, right? If I tell you, I have a table of size, billions and billions and billions, and the I cell stores value I, like you as the verifier understand what I'm saying without taking, billions and billions of time steps to like enumerate all the cells and values. Right. So, and these are the sorts of tables that arise in like Lasso and Jolt, to implement primitive instructions in RISC-V. Like the tables, the lookup tables that arise are enormous, but no one ever materializes the whole table. So that's one example. Another example would be like the RISC-V, like a RISC-V bytecode. Like this is like the program, the computer program, like the Jolt prover, will be, is claiming to have run correctly. Okay. And so if we every cycle of the RISC-V CPU, the CPU needs to know like what is the next instruction to execute or whatever. So it has to, like do a lookup into the bytecode. It's like I'm currently executing, line 76 of the bytecode. Okay, well, I have to know what line 76 of the bytecode is. So let me do a lookup into the memory storing the bytecode. Okay, and here, because we want people to be able to run like any old program, the multilinear extension polynomial of this read-only memory, also called a lookup table, is committed in preprocessing by an honest party. Okay, so these are the two ways that the lookup like the read-only memory contents get specified. Either the memory is like super structured and like kind of just like fixed in advance, and so in these settings, often no one has to commit to that table. This is sort of unique to some check-based lookup arguments that no one has to commit to that table, but that they achieve it. And then in other cases, we don't really have any information a priori about like what's in the table. So someone is going to have to commit to the table if you don't want the verifier to run in time linear in the table size anyway. And so that would often or typically be done by an honest party in preprocessing. So for the read-only case, what's actually committed to specify, is there are no writes to memory allowed, right? So it's just address value pairs. You say T of them, for reads, and the prover's claim is that, if we call the memory contents val, that val of address, equals value, for all pairs. Let's say if we got, T committed pairs, and this I is denoting which pair we're dealing with, the prover's claim for a lookup argument is that, the committed value for associated with any given address is actually the true value stored at the appropriate memory cell. Okay, so that's the problem we want to solve. Any questions?
Could you? Yes, question, please. Could you say a couple of words? Do we have in this case that you just explained a few polynomials as well as you were referring to 4 polynomials for right?
So in this case, there would be 2 polynomials, one specifying all the addresses and one specifying all the values.
Yeah, and so the question itself I wanted to ask was about I'm having some problem to understand how do we match address and value in this polynomial. Namely, I see that the degree itself would be a natural ordering to both. But why do we have polynomials? To have some kind of interpolation, and interpolation eats up all this degree ordering.
Yeah.
Okay.
So Twist and Shout use the sum check protocol and multilinear polynomials. Other memory checking arguments under the hood use univariate polynomials and stuff. And so, for today, because I'm presenting Twist and Shout, everything will be multilinear. And so, this is just like a very standard notion of multilinear extensions. So, what'd be going on is like well, let's talk about RV for a second. That's cleaner. So what we'd be doing is indexing, the committed values, there are T of them, by vectors in 0, 1 to the log T, and we'd be defining RV twiddle, which is the committed polynomial that specified the values, so that RV twiddle of I is, the ith committed value. So this is what I mean when I say, RV twiddle is the multilinear extension of, the committed values. And RV twiddle will be, committed with a multilinear polynomial commitment scheme. And so then our whole goal will just be to reduce the prover's original claim, which is, that the ith value is indeed the true quantity stored in the ith committed address. We want to reduce that claim to like a claim that RV twiddle of some random evaluation equals, something, and RA twiddle of some, random evaluation equals something else. And since RV twiddle and RA twiddle were committed, this claim can just be confirmed using the evaluation, procedure of the polynomial commitment scheme. Did that clear things up or no?
I guess I guess my question would be if univariate polynomial, if your univariate approach has something analogous to it.
Yeah,
With
I
this.
mean, you could try, and I would say you're just not going to get comparable prover efficiency. But you could define like a univariate, low degree extensions, where rather than indexing the addresses and values by, log T bits, instead you index them by, like T roots of unity in the field. And then, like the committed polynomial would be, I denoted with when they're univariate with like hats over it, so you'd map like the I such roots of unity to the address specified by the, field element I, or indexed by field element I. And similarly, like value, you'd be, would be the committed value indexed by I. So you're just changing, the indexing from bit strings to root to unity, and then changing the associated extension polynomials from multilinear to univariate, and nothing else really changes except that if you want a fast prover, you should be using multilinear polynomials and sum check instead of univariate things. It's just what leads to the fastest provers.
Um, uh, when values are committed, don't we lose information about ordering of the values?
No, because if I commit to RV multilinear extension, right? if I want to know what the very first, call it the zeroth, value is, I evaluate it at 0. So that's like the 0th, committed value. And if I want to know the next one, so this is the all 0 string. I would evaluate it at 0, 0, 0, 0, 1. And so the ordering is still there. If I want to know the final committed value, I'd evaluate it at all ones. Would be the the t minus 1th committed value. So the ordering's all still there.
So it is commitment to each value and not to 4 polynomials.
It's so there's, in the case of read-write memory, there'd be let's talk about read-only memory for a second. There'd be 2 committed polynomials. So RV twiddle tells you all the values and the ordering is there. And address twiddle would tell you all the addresses, and again the ordering is there. So you evaluate it at all zeros and you get the the 0th committed address. Now here this is assuming addresses are field element, but let's just go with that for a second. And address at all ones would be the t minus 1st committed address. So there's still 2 polynomials, one specifying all the values and one specifying all the addresses, but it's they're ordered. The ordering is there in the polynomial too.
Oh, thank you. We'll be looking at it further.
Okay.
So there's a question that says, like, if the index committed values are vectors of length 0, 1 to the log of t, why is it log of t?
That's just because, so like, there are t committed values in the read-only case. And so we want to be,
we're interpreting those as coefficients of a multilinear polynomial over n variables, and so t equals 2 to the n.
Yes, exactly. Yeah. Right. So you want to be able to assign each of the t committed values a unique binary string. So what's the appropriate length of the binary strings to let that happen? It's log t, right? Because the number of binary strings of length L is 2 to the L. So we want 2 to the L to be t. That means L is log t.
And I also was kind of wanting to understand, like, how does it? Oh, I just said that those entries correspond to the coefficients of the multilinear extension, but that's not right. They correspond to the outputs over the hypercube, right? And
yes,
then
exactly. They are evaluations over the hypercube, which you can equivalently think of as coefficients, but just in this other basis called the Lagrange basis. Yeah.
And there's another question that says, when you wrote val of address equals value, address and value are polynomials, right?
Yeah. So if I leave the tilde out, tilde means it's a polynomial, and no tilde means it's the vector that the polynomial is extending or encoding, right? Cool. Yeah. So this, I mean, like the ith committed value. There's no polynomial here, and this, I mean, the ith committed address. There's no polynomial here, and this, I mean, the true, lookup table.
Not polynomial, like value.
Yeah, but then the way these things are actually committed is you take these multilinear polynomials that extend the non-polynomial values, and you commit to the polynomial.
So in a sense, like, it's like technically, like, as written, it's not. It may not be a polynomial, but we're often switching between interpreting data as polynomial and back.
Yes, exactly. It's like if I want to commit to a bunch of data in any of these snarks, like how do I actually commit to that data? Is I find I take the polynomial that encodes the data and I commit to the polynomial, right? And then that polynomial, specifies the data, and the data also implies the polynomial. So we just kind of move back and forth as if they're the same thing when, they're not literally the same mathematical objects, but what one tells you the other and vice versa. So, yeah.
And I have a little thing here. I understood why I was asking about reordering, because the previous session a few weeks ago that you gave on lookups involved reordering, and when it was there, then the order of the things obviously was lost. So it was confusion about this different technique. Uh, and what I wanted to ask is what roughly the size of commitments here we are talking about.
Yeah, so in the zkVM context, which is obviously very popular today, and the main context where at least the read-write memory arguments get applied, the here are the typical parameters, right? So like T, well, ideally it would just be like the number of CPU cycles that the computer program runs for. So maybe I'll call it VM cycles that the VM runs for. So it's like the number of time steps that the computer program that the prover is claiming to have run correctly runs for. Okay. And then K, which is the memory size, is appropriate memory size. It depends. So both of these can vary a lot, right? So like in RISC-V, there are like 32 registers, and one of the or three of these 32 registers are accessed like almost every cycle, right? So we're Jolt, we're definitely going to be applying like twist to those 32 registers, and they'll be treated as a separate memory because twist gets especially fast when the memory is small. And so if your VM is hitting the same 32 registers over and over again, it makes sense to just treat them as a special, separate memory to get the performance benefits of having such a small memory. But the VM also has random access memory. A lot of programs might use megabytes of memory. Others might use gigabytes of memory. So this would be like megabytes would be like 1,000,000. K is 1,000,000, gigabytes would be K is like 1,000,000,000. So the whole gamut of memory sizes, are relevant. And in fact, the way Jolt uses lookups internally, it actually makes sense to talk about memories of size 2 to the 64, which are so big, that no one is going to materialize them all. It's like this range checking table I mentioned before, where the ith memory cell stores value I. And so, you can define that table to have size 2 to the 64, and no one's ever going to have to write down, 1, 1, 2, 2, 3, 3, all the way up to 2 to the 64. So K can kind of go from as low as 32 to as big as 2 to the 64. Let's talk about T for a second. Some computer programs might only, if they're very, very simple, they might only run for like 2 to the 30 cycles. Others might run for 2 to the 50 cycles or more. And if you are in a situation where the program runs for 2 to the 50 cycles, as of today, you would have a problem with any existing zkVM, whereby if you kind of directly try to prove all 2 to the 50 cycles at once, the prover will need like exabytes of space, and you won't be able to generate the proof. So what people will do is break these 2 to the 50 cycles into, say, 2 to the 30, shards, each, covering only like 2 to the 20 cycles. And they'll kind of prove each, shard of size 2 to the 20 separately, and then like aggregate the proofs in some way. And so that sort of means that while, we really would like to have T be 2 to the 50, because that's how many cycles the computer program actually ran for, we just can't do that. And so we sort of force T to only be 2 to the 20. And then, we're still left with a nuisance of then like aggregating, the statements about the 2 to the 30 different shards together. So I would say, as of today, maybe think about T as like 2 to the 20. But K really could be anywhere from, tiny, like a, 32 up to, a billion or even a billion squared. Is that clear enough?
Yeah, that's out of color. Thank you. And the commitment size is it usually logarithmic?
Yeah, so I'd say it depends what commitment scheme you use. But for most of them, the commitment will just be like one group element or one hash value, which is tiny. But then at some point you're going to have to evaluate, these committed polynomials, and so the evaluation proofs are where you might get hit with something big. So I'd say on the group, if you're using a group-based commitment, say like log many, order log t many group elements. And if you're doing a hashing based thing, it's polylog or even worse maybe. So let's if you're using like Frobenius, it would be like lambda log squared t hash values or something. So the commitments themselves are tiny, but the evaluation proofs are where the verifier is going to get hit.
I see. I see. Thanks a lot for the context and setup.
Great. Yeah. No, thanks for the question. So yeah, so like you're committing to like size 1 million objects, if T is like a 2 to the 20, but the evaluation proofs are, rather than 1 million group elements, they're only like order 20 group elements, something like that.
Question from chat.
Okay.
How does the prover commit to the table if the table is never materialized?
Great. So if the table is hyper structured, like, this range checking table, whose ith entry just stores the field element I, the table never has to be committed at all. Okay. By the way, this notion that like there are these very big objects, but the objects are never fully materialized, that is like the power of SumCheck. I mean, you can see it like to I think a slightly lesser degree with univariate polynomials too. But SumCheck's incredible power is kind of summing over enormous objects without kind of anyone ever paying for materializing the full objects. In the other example I gave of RISC-V bytecode, which is basically like a computer program, there the memory would not be so big, right? Like everyone does have to actually know what computer program is being run, so they do have to actually, someone has to, or at least the prover has to store the bytecode, and so there's no problem with having someone just like commit to the bytecode. Did that clear things up?
Thanks.
Great. Okay. Maybe I'll say one more thing before we get to how the twist and shout work. This might be confusing, but I think it's also getting at the power of SumCheck. So the way I formulated, say, lookup arguments, I said the addresses and the values were committed. Yeah. Well, it actually turns out that, so I'm just going to state this as a fact. Like the snark verifiers only need to know one random evaluation of each of these polynomials RV and RA. Okay. And moreover, if I tell you the lookup table val, if I tell you, hey, the memory cell stores value I, so if I tell you the table and I tell you the addresses, Okay, I've actually implicitly, specified the values, the correct values, right? I've also told you implicitly the values, right? The if I fix the table and I fix the addresses of all the reads, there's one correct value returned by each of the reads. Okay, so in principle, actually, RV twiddle does not need to be committed. Okay, but and moreover, and the snark verifier only ever cares about evaluating RV twiddle at a single point R. Okay, so twist and shout actually do not need the values to be committed. I said RV twiddle is committed because it makes it easier to define the problem. RV twiddle will not be committed. What will really give, like what shout really is just a fast way, to reduce the task. Sorry, this is so squeezed here on the iPad. To reduce the task of evaluating RV twiddle, so of computing RV twiddle at a point, to evaluating, just val twiddle and address twiddle at a different point. Okay, so that's how you're able to avoid even committing to the values. Is like the snark verifier only needs to evaluate the multilinear extension of the values at one point, and we're able to give kind of express that evaluation. I call this a virtual the Binius guys introduced the terminology of virtual polynomial. So it's like a polynomial that the prover does not commit, but that the verifier can sort of pretend is committed. And then when the verifier needs to evaluate the virtual polynomial at a random point, you have to give a way to kind of relate the needed evaluation of that polynomial to an evaluation of polynomials that were committed. And that's really what shout is. Okay. So that's an extra nice savings on commitment costs. The shout prover never even has to commit to the values. It only winds up committing to the addresses. That's it. Okay. I hope that made enough sense. It's a little hard to wrap your head around.
Question in chat: what's the difference between val and RV?
Yeah, sorry. I maybe shouldn't have used the vals are like the true values. And RV, if it was committed, I just told you it didn't have to be committed. But if it is committed, RV is like the claimed results returned by the reads. So I would say val is like just the lookup table. RV, this stands for read values. Okay, so this is saying, hey, the ith read operation return value I. This val is the actual values in the table, the true values in the table.
Question: so RV is RV like the oracles ERX and ERY in Spark?
Yes, except those actually need to be committed, I think. So yeah, those need to be committed. And the reason, okay, sorry. Spark is okay. Because I'll give a little context so people understand my answer, even though the question asker obviously has this context. Spark is what's called a sparse polynomial commitment scheme. So it lets the prover commit to a polynomial that's very, very sparse, meaning most of its coefficients are zero, and kind of never really pay for the zeros, if you will. And so the challenge is producing evaluation proofs in time that grows only with the non-zeros and not all the number of zeros. And so what Spark winds up doing is a bunch of lookups into a certain lookup table. And so these ERX and ERY polynomials that the question asks about, those are exactly the values returned by those lookups. Okay, now the lookup argument used in Spark was lasso. Now, lasso came later. So really, lasso was like, we came up with lasso by looking at Spark and being like, well, what is Spark really doing? Said, oh, there's a lookup argument here. That's lasso. So this is, yeah. Spark uses lasso as a lookup argument. Okay. When using lasso as the lookup argument, or really anything before shout, these values would need to be committed. The whole polynomial needs to be committed. And that's just because of, how lookup arguments other than shout work internally. But in shout gets rid of that. So actually the twist and shout paper give, I guess we call it Spark plus plus. It's a sparse. All we do is we take Spark, we replace lasso with shout. Okay, and we immediately cut out, reduce the prover's commitment cost. I don't know, massively. So I think it's like maybe the prover commits to, I don't know, 1/3 the number of values, by cutting out the need to commit to the RV polynomial. But actually, in the context of Spark, these values are random, so they're like really, really expensive to commit to. And so we when we cut out 1/3 the number of values, we actually cut out all of the random values, and all that's left is non-random values. So this is actually more like a something like a 30x speed up in commitment time by doing this. So great question. So yeah, the ERX, ERY polynomials in Spark, that's exactly this RV stuff. But by using shout, you no longer need to commit to the RV stuff. The prior lookup arguments do not avoid committing to the RV stuff. Other questions? All right. Okay. So thanks for all the questions. I think like perhaps the hardest part about discussing and presenting memory checking arguments is just formulating the problem. So it's possible we've gone through the most difficult part of today. Now I'll tell you how shout works. We actually came up with twist first. But shout is simpler in hindsight. So let's do it. So there's this funny thing where in prior lookup arguments, the address is one address was one field element. Okay, shout is different. Okay, so before, if you had like k equals 2 to the 20, that's like 1 million memory cells. They would be indexed with, like if you look inside Lasso, like the way you tell Lasso what memory cell you're reading, you would just write down one field element. So indexed by field elements between 0 and like 2 to the 20 minus 1. Okay, in a binary field, it would just be, sub, like, the GF 2 to the 20 subfield or something in a binary field. So whatever, you just come up with your favorite, 2 to the 20 field elements, and assign each memory cell one of those 2 to the 20 field elements. So in shout, we use what's called the one-hot encoding. So in shout, one address is actually a vector of length k. So this would be, if your memory size is 2 to the 20, that means every address is actually a length 1 million vector. Okay, which sounds terrible, because that vector is so long. But because it's so long, this vector is incredibly sparse. So these vectors are unit vectors. So it's like, here, let me just set k to be 4. Right. So then, to say, hey, I want to do a read into, this memory cell here, the address here would be 1000. If I wanted to say, hey, I'm going to do a read into this memory address here, this one here, the address would be 0010. Yeah. So just sort of the unique one in the vector is telling you, hey, this is the memory cell I care about for this operation. That's what one-hot encoding means. Okay, and the key, I guess, key fact, the reason it's not crazy to use to specify addresses in this way is the following. Like, let's say, net, for a lookup argue, if I'm doing T reads into memory, this means I'm going to have to commit to a length. I need to commit to a length k times t vector, right? Because I have t addresses, and each one is actually specified by a length k vector, albeit a very, very sparse one. So to commit to a length k times t vector with, that's all zeros except for t entries that are one. To do that with any curve-based commitment scheme, so Dory, bulletproofs, whatever. So I can actually do that with only T group. Actually, it's T minus one, but whatever. T minus one group operations. Okay. So committing with these Peterson vector commitments that we discussed for several weeks until last session when we switched over to hashing-based commitments. It's like zeros just literally do not affect the commitment, right? If you remember, like the commitment to a vector X was with these curve-based things is like group product from over all entries of the vector of gi to the xi. And so if xi is 0, well, gi to the xi is 1, and it just literally doesn't change the product. Xi equals 0, just filter it out. Ignore it. It literally doesn't, it contributes a 1 to this product, and multiplying anything by 1 doesn't, it's a no-op. Okay, and so it's not so bad to commit to giant vectors if they're very sparse. Okay, now there's some subtleties here. It's like you can't like just kind of commit to insanely giant vectors and like never pay any price for that whatsoever. So let's call this the sparsity, meaning the number of non-zeros, and let's call this the size of the committed vector. Okay, so where does the size actually hit you in a curve-based commitment scheme? The size of the vector you commit to, it hits you in two ways. The most important way, as I'll explain shortly, is the commitment key grows with size. So it's sort of like saying, hey, I don't know, the prover knows in advance that it's going to only have to commit to, T1s, but until it runs the computer program and figures out what reads were done into memory, it doesn't know where those T1s will be. So it kind of needs to be prepared for those T1s to be anywhere in the whole vector. And so the commitment key, needs to be prepared to commit to, like kind of doesn't benefit from the sparsity. You kind of have to be prepared for the ones to be anywhere. So the commitment key grows with the whole size of the vector, no matter how sparse it is. Okay, so that's sort of the most painful way that the size creeps into like the snarks costs. And this is why I've been saying for the last several sessions that it's a really nice property that schemes like Hyrax and Dory, which are curve-based, have sublinear size commitment key. So their commitment key is roughly like square root of size group elements. If you look at bulletproofs or hyper KZG, or zeromorph, they have linear size commitment keys, so like size many group elements. Okay, so what that means is they're more restricted in terms of how big this k times t can be before you're just like your commitment key isn't prepared to deal with vectors of that size, no matter how sparse they are. So that's one way that committing to these giant but very sparse vectors that you actually pay for the size and not just the sparsity. The other way is that the evaluation proofs cost the prover operations, time that grows with size. Okay, and so in the same way that Hyrax and Dori achieve sublinear size commitment key, they also achieve sublinear time evaluation proofs. And explaining that in full detail is a little nuanced. So let me just say I'm waving my hands just a teeny bit here. So that's another really nice thing about Hyrax and Dori. And the hashing-based commitment schemes like Fry and not Fry necessarily. No, Fry is linear time. Like Binius and Breakdown and Ligero have similar nice properties to Hyrax and Dori. The reason this sounds like the situation with like commitment key size and evaluation proofs are about the same, and maybe these two issues should be equally concerning. But there are other tools at our disposal to drive down the cost of computing evaluation proofs further. So just as an example, it's sort of Hyrax and Dori kind of exploit these sorts of things internally, right? It's like let's say I wanted to have the cost of Bulletproof's evaluation proof computation, because that is really, really expensive. So like what I can do is I can rather than Bulletproof committing to one vector of size n, I can separately Bulletproof commit to two vectors of size n over 2. So I can Bulletproof commit to each of them separately. Okay, and then it turns out when I want to evaluate the size n polynomial at a random point, say r1 comma x, maybe I'll call this q1 and q2. These are the polynomials committed here. P of r1 comma x is the same as 1 minus r1 times q of x, q1 of x, plus r1 times q2 of x. Okay, so what the verifier can do is it can homomorphically, compute. So the verifier on its own can compute a commitment to 1 minus r1 times q1 plus r1 times q2. That's exactly what homomorphism lets you do. It can compute this commitment even though it doesn't know q1 and q2. It only knows a commitment to q1 and a commitment to q2. And so then the prover, can provide a proof for the evaluation of maybe let's call this thing q prime of q prime of x, right? And the key point is q prime it's a single polynomial size n over 2. And so we just have the cost of computing the evaluation proof by doubling the size of the commitment compared to vanilla Bulletproofs that would produce one commitment for a vector of length n rather than two separate commitments to vectors of length n over 2. We were able to we doubled the size of the commitment from one group element to two group elements, but we in return we have the cost of computing evaluation proofs, and folding schemes like Nova and so forth do something like this sort of on steroids. By on steroids, what I mean is here we did the good thing we got was cheaper evaluation proofs, but we did pay a price for it where the verifier costs went up because now there's two group elements rather than one in the proof, and the verifier has to do these scalar multiplications to get a commitment to their linear combination. And folding schemes kind of avoid the increase in verifier costs that we see here by bringing in recursion. So for all of these reasons, basically, I would argue that you can just forget about the evaluation proofs, the runtime growing with the size of the committed polynomials. That just is never really a major bottleneck. It's this commitment key size to focus on. Okay, so let me pause there. But as we'll see, like as soon as you're prepared to commit to these one-hot encodings, life gets really easy. So using, committed one-hot encodings of addresses is what we'll talk about next. Okay. But what I've said till now is, while these, one-hot encodings are huge vectors, they're very sparse, and so committing to them can be really fast, no matter how big they are. That's the summary of what we've talked about thus far. And before we go on to then how do you actually take advantage of that? Any questions?
It seems to me that one-hot encoding enables only one write operation, or maybe read operation. I mean, you can't address a slot several times with it, or can you?
Yeah, so you can. The way to think about so let's talk about the read addresses getting committed. Okay. So let's say, first you want to let's say, I don't want to say this. So what, the vector, I go between saying, oh, it's a committed vector, oh, it's a committed multilinear polynomial. They're all the same. So let's use the vector terminology right now. So this committed vector, what it is, it's a vector of length k times t. Okay, and so you can think conceptual. You should conceive of it as arranged like a matrix, even though it's committed as like one giant vector. Okay, and so there would be k columns and t rows. Okay, and the ith row, the ith row here is just the one hot encoding of the ith address. Yeah. So if like every single one of the T reads could be to the same cell and there's no problem, right? Like let's say, every you just read, cell 2 over and over again. Then this committed vector RA would just be, 0, 1, 0, 0, 0, over and over and over again. And so there's nothing stopping you from reading the same address, many times or writing the same address many times. It's just, this thing will just have many rows that are the same. Then that's fine. Did that clear things up?
Yeah, I thought it was a different thing.
Okay. Yeah. Yeah. So it's just like a funny way of specifying addresses, just a very sparse way of specifying addresses. So there's no restriction on, like, so when specifying a single address, yeah, like, there's only going to be one, but that's no problem because, if there are k memory cells, only one address is being read, and so the ability to stick one in any one of the k slots lets you, specify an arbitrary one of your k memory cells, no problem. And then between rows, between addresses, there's no reason you can't have repetitions, just reading or writing to the same address multiple times.
And each row here will always have only one.
Yes.
Oh,
Yes, but shout itself is going to have to get a guarantee of that. So you can't just assume that, because then the prover could mess around and commit to something that is does not have every row be a unit vector. And in fact, we already have implemented shout, like the simplest variant of shout, and the most expensive thing is exactly just making sure that all of these rows are unit vectors. Actually, the most expensive thing is just making sure that all the entries are zeros and ones. So that it would be, you know, really nice if we could somehow just like assume that everything committed was every row committed was a unit vector. But right now, I don't know how to do that. I think you have to run some sum checks to get the guarantee.
Thank you. That explains a lot. Thanks.
Yeah, great. Thanks for questions. Other questions? All right. Okay. So, oh, is there a question?
Yep, one chat.
Okay.
So RA and RV are one hot encoded, and then they index the address and val lookup tables respectively. Is that right?
Oh, no, sorry. This bringing in this valve notation is confusing things, unfortunately. So apologies for that. I guess I shouldn't have done that. So only the addresses are one hot encoded. Okay. So our RA is in where the one hot encodings come in. RV. So firstly, I guess I can say two things about this. One is it's not committed at all in shout. Because the verifier is ultimately only going to, I don't know, it's kind of going to pretend it's committed, but it's not. And when the verifier needs to evaluate RVR at a point, RV at one point R, you use some check to reduce that to evaluating just RA tilde. But the other thing, it doesn't really make sense to one hot encode the values because they twist and shout in any memory checking argument that I know of is actually prepared for the values to be arbitrary field elements. And so, one hot encoding them would mean, field size many or -1 many zeros and 1 1, which would be, this is not okay. If you're working over a field of size 2 to the 128 or 2 to the 256 or something, that's just too big. Like I said before, the size of the sparse committed things does affect you somehow with these commitment keys and evaluation proofs. So anyway, so it's the addresses that make sense to one hot encode, and this means the one hot encodings have length k. K is the memory size, whereas which turns out to be okay. Length field size would not be okay. Did that clear things up and make sense?
Hang tight.
Okay, great. Yeah. So you can one hot encode the addresses, and it's sort of okay because there are only k possible addresses, whereas the values there are field size many possible values, and so. Firstly, I don't think you would benefit from one hot encoding the values. I mean, it'd be interesting to think about, but also you just can't. The one hot encodings would just be too big. Okay, and then yeah, great. So I think hopefully that answered the question. More questions?
Nope.
All right, great. So once you have these one hot encodings, and you do have to again check that they are valid one hot encodings, and that alone requires some check magic. But let's brush that under the rug right now, not dwell on it. Once you know that it's one hot encodings that are committed, life gets really nice, at least on the surface, because now. If we're focusing on the lookup case, which is what Shout focuses on, like the condition that RV twiddle of I here, this is I and 0 1 to the log t, meaning the ith lookup. So RV twiddle of I is correct. Remember that's equivalent to vals of the ith address being equal to RV twiddle of I, right? Like remember the claim the prover's making is that the ith committed value, even though RV twiddle is not committed, the ith committed value is equal to the true value stored at cell given by the ith committed address. Okay, and so this is, with one-hot encodings of the addresses, this actually turns into just a rank 1 constraint. Okay, so another way of writing this is that, let's see, a few ways you can, let's say the sum over memory cells of the one-hot, how do I say this? Sorry, sorry. J, let me get this right. So we're dealing with the I3, yeah. So we'd want memory cells K of vals K times RA KI equals RVI. Yeah, okay. So yeah, so what's going on here is this term RRA of K comma I. So this is memory cell K, and the I times cycle. Remember, we conceptualize the RA as like a T by K matrix. So with so here K is specifying I guess row or column, and I is specifying the other one, column or row. And so this is going to equal 0 if cell K is not the cell read at cycle I, and it will equal 1 if cell K is the cell read at cycle I. Right. That's what one-hot encodings do. Yeah, is like it says, spit out a 1 just for the cell that's actually read here, and everything else spit out 0. Okay, so this equals 0 thing means you kill vals K for all K except the 1 K that's actually read at cycle I, and then the sum just spits out the true value for that cell. Okay, and that's exactly what RV of I better equal, right? RVI is supposed to be the value stored in the cell read at cycle I. Okay, so this is a rank 1 constraint, and there's one rank 1 constraint per cycle. So what we have here is T rank 1 constraints. Okay, and we have really good snarks for rank 1 constraint systems. Okay, so roughly speaking, Shout would say just apply, one of these known snarks, say Spartan, which is a sum check based snark for R1CS to this R1CS instance. Okay, that's it, right? So what's going on is like as soon as you have these one-hot encodings, everything is low degree and in fact rank 1, and life is super simple. Okay, in fact, this kind of observation was already somewhat implicit in earlier lookup arguments, but they all ran into issues that I'm about to flag, and that Shout gets around. But let me just see if there are any questions about this constraint here.
None in chat, so it looks like no.
Great. Okay.
One might be coming in.
Okay.
So Shout uses Spartan, but Spartan plus uses Shout.
You do wind up with some of these confusing things, but so Shout uses Spartan, but heavily optimized to this particular constraint system, and then Spartan uses Shout to speed up lookups that are done Yeah. Okay. Sorry. How do I want to say this? So shout applies Spartan to a highly uniform R1CS. This is like an incredibly structured constraint system. Okay. Spartan and Speedy Spartan, which are two Spartan variants we give in the paper that use shout, they are targeted at non-uniform constraint systems. Okay. And so the way that Spartan changes and improves on Spartan is inside how Spartan dealt with the non-uniformity. So you could say Shout uses Spartan for uniform constraint systems, and in fact does extra optimizations given just how uniform this constraint system right here is. And then Spartan uses Shout because when Spartan is applied to non-uniform constraint systems, internally you wind up with some derived uniform constraint system, and that's exactly the situation that Shout, or the way Shout uses Spartan is useful. So we maybe you get rid of the circularity, I think, the seeming circularity, if you realize that kind of Shout uses and extends Spartan for uniform constraint systems, and Spartan improves Spartan for non-uniform constraint systems. Hopefully that was somewhat followable.
Does uniform just mean one non-zero per row in constraint matrix?
No, generally when I say uniform, what I mean is the multilinear extension of the constraint matrices is efficiently evaluatable, which is actually guaranteed by much weaker structure than this, uber sparsity situation. But so I would call this like super structured. It's like, look, Spartan only uses a sparse polynomial commitment scheme if the MLE of the constraint matrices is not quickly evaluable. This constraint system not only has that property, it has way more properties. It has this every row of the constraint, I don't know, it has this like super sparse situation going on that's like kind of a even more powerful form of structure than kind of uniform Spartan versus non-uniform. More questions?
Is the constraint system one row per cycle in each column being the memory cell?
Yeah. So if you were to write this out as matrices, A Hadamard, AZ Hadamard, entry-wise product, BZ. I'll tell you what the dimensions of these matrices are in a second. Minus, some CZ equals 0. So the number of rows, which is the number of constraints, is T rows. Okay, but the number of witness variables, which is the number of columns of these matrices, as well as the length of this vector Z, is K times T. Okay, and that's exactly why, you can't just say, well, apply Spartan and you're done. Yeah, because we cannot afford the prover to spend K times T field operations. And if you just sort of apply Spartan in a totally black box way, even though these matrices A, B, and C are like super duper structured, you would still have some costs creep in if you're, naive, that depend on the number of columns, which is K times T. In fact, yeah, so there would be at least a K times T cost to the prover, and we're not happy with that. Did that answer the question?
Wasn't the sum above over K and not KT?
Yeah. So each constraint. So there's one sum here per constraint. So that means there are T sums total. And so each constraint involves a sum over K terms. So, I guess the way this looks is, I might get the picture a little bit wrong here, but we have T rows T times K columns. But if you look at each row has T1s. Okay, and so the number of non-zeros in A is actually sorry, not T1s, K1s. The number of non-zeros is T times K, right? So there's T times K columns and there's T times K non-zeros in total, kind of split across T rows, K non-zeros per row. That's what's going on here. Does that clarify further? So that they're K1s per row because the sum is over K terms in each constraint. Does that clear it up? So that yes, this sum is over K terms. That means each row of these constraint matrices has like K1s in it, and there are T such rows.
Yep.
Great. Okay.
I'm really sorry. Could you just remind us? K is the memory. How much memory do we got? T is how much addresses?
So T is number of lookups or number of cycles. So for read only, that would be number of reads.
Number of words, yes. And my question was if it can be less than K once. Is it? I mean, not every memory would be
Yeah. So
accessed every
I would
time.
say that there are ways. So you're asking can there be dummy read operations that don't read anything? Was that the question?
Not quite. If there are K ones, does it assumes that every register, every address is read at least once? I guess that's how we got K in the
I
beginning.
see. No. So every K1s per row. These ones are coming in because the constraint sums over all registers. So these constraint matrices are fixed. There's nothing kind of dependent on the actual reads that occurred in them. The solution vector Z, this vector Z here, that's the solution vector. This Z is, let me think for a second. Yeah, I mean, I think that the addresses that are read are in that vector Z, and those addresses are specified by one-hot encodings. So, we're sort of guaranteed that, there are exactly T ones in Z, just because, we've confirmed, that via external proof machinery that all the committed addresses are indeed one-hot encodings. Yeah. So so talking about these constraint matrices A, B, and C for the R1CS, those are just fixed. I mean, all I need to do is tell you like capital K and capital T, and you immediately know what A, B, and C are. It's Z that involves the actual reads that actually are being checked. A, B, and C are sort of agnostic to the actual reads that are actually being checked. So this is the constraint system, right? I don't. Okay, so I've never actually drawn the whole picture of the constraint system out before because you don't. I just kind of look at this this sum here and apply sum check to it, and there's no need to actually use the R1CS formalism. So I guess these vals things are coming up somewhere. So I don't think everything I was saying about these matrices brought in the table entries are somehow appearing in the constraints. anyway, so maybe what I said applies to like A but not B, because B involves, you know, these vals terms, and A only involves the address terms. Anyway, but in general, we have T constraints here, and but there are K times T witness variables, and we're really not happy with K times T prover time. That's kind of the main high level takeaway. Okay, more questions?
Nope.
Okay. So since we're, you know, pretty deep into today, I guess I'll just sort of assert, you know, claim, like you can implement the Spartan prover applied to this constraint system. You know, so it's like super structured constraint system, tons of sparsity everywhere, with order K plus T field operations. Okay. And so like, you know, you do, because you like this vector Z, you know, has length KT, has length K times T. This means, you know, you do wind up, you know, so its entries would be indexed by, you know, 0, 1 to the log K by 0, 1 to the log T, you know, and so sum check, you know, does involve, you know, summing K times T terms, and, you know, log K plus log T rounds, you know, because there's one round of sum check per variable, and we do have, you know, our variables are indexing into a K times T sized object. But, you know, it turns out that like in each round, at most T of the terms, you know, so you're summing up a huge number of terms, but very few of them are non-zero. And in sum check, like you just turns out you don't have to pay anything on the prover side for 0 terms. So this dates back to, you know, some old work of mine on the GKR protocol. Not that's 2012. And you know, you take the same ideas and techniques and kind of apply them to this particular sum check, and this all falls out. And in fact, well, let me think. There's some other really nice properties here, which is like actually the first log K rounds, I think you can get through, like the prover can get through these rounds, I think, with just like order K space. And so, like, you know, I'm looking ahead a little bit. I think, you know, these new protocols are actually going to help with keeping the prover space low, not just have a fast prover, but you know, so yeah, it's really, it's like the first, it's like before the protocol even starts, the prover algorithm that achieves this order K plus T time bound, kind of you know, goes like, think of K for now as like smaller than T. So you in the early rounds, it's like any read to cell K kind of acts the same, and so you can kind of you know, if you take all of the reads to cell K if you're the prover, and aggregate them together into a single quantity. And so no longer in those first K, you know, as soon as you do that aggregation, which costs, you know, like, you know, what, like constant time per read, you now are only dealing with a size, like one value per cell, you know, so like a size K object from that point. And like that's enough information, like one value per cell, to get you through the first log K rounds of the protocol. Okay. So you kind of just do this linear time in T aggregation procedure. That's enough to sort of get you as the prover through the first log K rounds. And then after those log k rounds are done, kind of everything has collapsed to just a size, you've gone from a size k times t vector being summed, it all gets collapsed down after log k rounds to a size t vector. Okay, and so then for the final log t rounds, you can just apply standard linear time sum check proving algorithms that will implement the prover in time order t for the final log t rounds, just as completely standard. Okay, so waving my hands here, but that's it. So the key, we're sort of avoiding paying for not for zero values twice. Okay, so when the prover commits to addresses, by using one-hot encodings, we are like the vectors that get committed are very, very, very big, but very, very, very sparse. And using an elliptic curve-based commitment scheme, the prover time sort of only grows with the sparsity and not with the zeros, the number of zeros in those vectors. So the commitments, choice lets us avoid paying for the zeros on the prover side. And then the sum check protocol lets us, deal with this very, very large constraint system. But like most of the witness variables in this constraint system are zero, and the sum check protocol lets us avoid, paying for the zeros there as well. So you don't pay for the zeros when committing, and you don't pay for the zeros after committing either. So that's kind of shout in a nutshell, with apologies to not present the whole sum check prover algorithm. Okay, let me pause there. Does anyone want to ask questions about that?
Looks like nope.
Great. Okay. Okay, so let me just collect my thoughts for a second. So I could do one of two things. I could compare shout to prior lookup arguments, or I could just move on to sketching how twist works. Probably I should compare shout to prior lookup arguments a little bit.
I think those sorts of those higher level comparison things are kind of one of the places where this study group is an opportunity for you to really share your insights that you can't really get elsewhere.
Great. Okay. Perfect. So, we've discussed this before several times, although I've never covered the details well. But prior lookup arguments, they always worked as follows. So they would prior work. So they would reduce the claim that all reads are correct. That means that the ith committed value indeed equals the true value stored at cell given by the ith committed address. So they would reduce that claim to an equivalent claim that two vectors are equal are permutations of each other. So let's just call them A and B. Okay, and then the way they check that claim is they would interpret the entries of A and B as the roots of a univariate polynomial, and just evaluate those two polynomials at a random point, and confirm that the evaluations are the same. Okay, so they do. The way they would check that A and B are permutations of each other is the verifier would pick a field element R at random and check that the product over all entries of A of AI minus R equals the product over all entries of BI minus R. Okay, and so this basically what we're doing is we're interpreting the entries of A as roots of a univariate polynomial and interpreting the entries of B as roots of a different univariate polynomial. And two vectors are permutations of each other if and only if these are the same polynomials, right? Because once I tell you a univariate polynomial's roots, I've told you the univariate polynomial. And so this is just, evaluating 2-degree n polynomials at the same random point R. And so, if they're not the same polynomial, they agree at a random valuation only with tiny probability. So yeah, this is like a randomized way of checking that A and B are permutations of each other. And so different lookup arguments differed in how, like, what these vectors A and B were. But they all worked in this way, and the only way they differed was how A and B, what they are. So there's some way to take all of the looked up values and looked up addresses and turn them into these two vectors A and B. But everything turned them into some vectors A and B, and then did this same permutation check. Okay, so in that way, everything boils down to computing these two big products. This is called a grand product. Grand product is when there's a whole bunch of committed values, and the prover makes a claim as to what the product of all those values are. And so this, in all existing lookup arguments, this grand product would be over at least k plus t terms. So like this n here would be at least k plus t or bigger, basically. Okay, and so now you have a bunch of options regarding how you compute this grand product, or these two grand products. Okay, if you're using the SumCheck protocol, your options were basically apply the GKR protocol to a circuit computing the grand product. That would just be like a binary tree of multiplication gates. Or you could apply Spartan, or really Clover. Clover is a much earlier protocol than Spartan to the circuit. And basically, the GKR prover would be faster than the Spartan prover by a lot because it commits to less data. But the proof size would be like log squared n, whereas the Spartan proof size would just be log n. Okay, and then your third option would be to use univariate, apply what's let's say what some people call univariate SumCheck, which I think is a confusing name because it works nothing like the standard SumCheck protocol. Univariate SumCheck here refers actually to the problem being solved, is univariate analog of the problem that the standard SumCheck protocol solves. The univariate SumCheck protocol is totally different than the SumCheck protocol. And here the proof size could even be smaller than log n. It could even be constant, depending on your commitment scheme. But the prover is even slower than Spartan or GKR. So you kind of have the whole gamut of fastest prover up here but biggest proofs, down to slowest prover down here but smallest proofs. And I could go into the weeds about if you use Fry instead of a group case thing, then actually these proofs are pretty big even down here, and stuff like that. But this grand product, this appears nowhere in Shout. Okay, and that's really where the benefits of Shout come from. So asymptotically speaking, so Shout proofs are log size because you just apply SumCheck once. Okay, so like Spartan applies SumCheck once or maybe twice, depending on how structured the constraint system is. And Shout, of course, is Spartan-like, and so Shout achieves the proof size of the Spartan approach, but has an even faster. So Shout is a faster prover even than the GKR approach. So it's like it achieves the Spartan size proofs with more than a 10x prover speedup. Okay, and if you compare it, so it's maybe 3 times faster than the GKR protocol for the grand products, but like 20 times faster than Spartan for the grand products. So you could view all of the benefits of Twist and Shout as coming from just getting rid of the grand products. Now let me think if there's anything else I want to say there. Maybe I guess anything else I'd say is in the weed. Like getting rid of the grand products is also why for Shout we don't have to commit to the values returned by the reads. And that, as we've discussed, that has major implications. I'd say in the ZKVM context, that's kind of a nice to have, but not like a make or break, like a major prover speed up. Maybe, think of it as like a 10% prover speed up. In the context of Speedy Spartan or Spartan plus plus, it's a huge deal, right? Because lookup arguments are applied in those settings. At least in the Spartan plus plus case, the lookup argument is applied to a table storing random values, and so committing to those values is extremely expensive, because committing to random values is really pricey, whereas committing to small values is an order of magnitude faster. So so somehow just like leveraging sparsity within twist and shout seems to be the key. It's like, well, once the prover is committing to these sparse vectors, we have ways to avoid the prover paying for all those zeros. And it's like these grand product things was just they weren't leveraging sparsity anywhere really. They were kind of trying to turn everything like as dense as possible, and it's like sparsity is the key. Have these very big but very sparse constraint systems and just avoid paying for the zeros, and that just seems to be the right way to do everything. By the way, one thing that annoyed me about these grand products, just from like a conceptual perspective, is if you look at something like Jolt, it was designed with multilinear polynomials and the sum-check protocol like as the first class citizen or whatever, the first order object. And there was only one place in the whole protocol that univariate polynomials came up, and here it is, the permutation check. Okay, and this was like a major bottleneck, this grand product, which was coming in because of a univariate polynomial. And so I've always felt like, univariate polynomials just have no business being in the protocol. There's got to be another way, and this seems to be the way. And then one more comment. One big nuisance about these permutation checks seem to benefit minimally from memories being really small. Okay, so you'd think like, RISC-V has 32 registers. That's like almost, that's tiny, right? Like laptops have gigabytes of space, billions of memory cells, but there's only 32 registers that are read and written like every single cycle of the CPU. So somehow like we intuitively, should be able to benefit from there only being 32 registers. And if you brought in this permutation check thing, you wouldn't. And why wouldn't you? It's because both these vectors A and B tend to have size like memory size plus T. And so, if the memory is small, well, you're still, paying for the big T everywhere. And like just the small memory is maybe buying you a factor of 2 or something at best. And so the way we actually came up with Twist and Shout was we were looking at Jolt and we were saying, okay, like long term, after we finish optimizing everything we know is optimizable, what will the prover bottlenecks be? And like the most extreme bottleneck was just reads and writes to registers. And it's because they're read and written every single cycle. There's actually, 2 reads and a write. And we had no way to benefit from the fact there's only 32 of them. And so, that's the context where one-hot addressing seems like not such a terrible idea, right? Like if committing to addresses means like 32 values, per address, that doesn't sound so crazy when Jolt itself, today commits to like 80 values or something per cycle. Right. So like if we were already committing to 80 values, maybe an extra, 31 values wouldn't be so bad, rather than committing to the address as a single field element. If you committed to it as 32 field elements, well, who cares, right? Like you went from 80 values committed to 112, whatever. So we came up with like Twist and Shout in the context of tiny memories where one-hot addressing wasn't such a big deal. But then it turns out that even if your memory is really big, one-hot addressing can still be the right way to do everything by, you then wind up with these giant sparse vectors, but you just never have to pay for the zeros. So, okay, questions about those rambling thoughts?
Looks like no.
Great. Okay. All right. So I'm going to I'm going to say one more sentence about shout, and then I'll probably try to say something about twist, but I'll keep it quick because, we're so far into the session. And yeah, I think next week maybe we'll discuss Fry or something. Not any brand new research. So we also introduce a parameter D for dimension, that helps control, the costs that do come in from these really big vectors. So yeah. There is you can't like I said before, like while the commitment key is like the limiting factor if you're using a curve-based commitment scheme that keeps you from easily handling billions and billions and billions of memory cells, right? Like there are some limitations that come in from having these giant sparse vectors, with commitment key being the biggest one for curves. So this parameter D can help with that. So the bigger D is, the smaller the committed vectors, or maybe I should call it shorter the committed vectors. Okay, but let's say the more work that the prover does outside of the commitments, it also means more work when computing the commitments. So it's kind of like you want to set D as small as you can to keep the prover's work outside of the commitments as small as possible. But you can only have a commitment key that's so big, right? So like make D as small as you can, but it's got to be big enough that your commitment key isn't so big that the prover can't generate or store it, right? So and where does this D come in? Okay, so basically with one hat addressing an address, so D equals 1 is sort of what I presented. An address is k minus 1 zeros and 1 1. Okay, so it's like a unit vector of length k. Okay, now you can take any unit vector of length k, let me call it, I don't know, e sub little k, and this can actually be written as the tensor product of, so let me call it e sub k1 to e sub kd, where each of these is, so this is a tensor, each of these is a unit vector of length k to the 1 over d. Right. So it's, now like kind of rather than viewing, memory as like one giant array of length k, if d equals 2, we'd instead view memory as like a matrix, a root k by root k matrix. And ek1 would be the one hot encoding of the column that you're in, and ek2 would be the one hot encoding of the row that you're in. So that's all that's going on here. And so we, what we do is we have the prover commit to ek1 up to ekd. And so now, rather than that being, one vector of length k with 1 1, so one unit vector of length k, we now have, d unit vectors of length k to the 1 over d. Okay, and in that way, it actually seems like with like if you use Dory as your commitment scheme, you can even handle like k equals 2 to the 64, which is what we use in Jolt today for all of these lookups that we do for primitive instruction execution. It's fine to set d to just be 2 with Dory, but like if you used something like bulletproofs or something that has like a linear size commitment key, you probably need to have d be like 4 or something with bulletproofs. Okay, this D is also makes it so that we can use Binius. So you can use Binius or Blaze But now the D's have to get pretty high. Like if you want to handle a lookup table size 2 to 64, you're probably going to want to set D to be like 16. Okay, and what's going on there is the way that like big sparse vectors like hit you in certain costs is very different for hashing based schemes and curve based schemes. So with curve based schemes, the big issue was the commitment key size. With hashing based schemes, the commitment key is always tiny. The commitment key just tells you what hash function to use. So the problem with Binius and Blaze is that zeros are not totally free to commit to. So it's like, if I have a vector that's mostly zeros, I still can only pack, 128 zeros into one field element. So I kind of pay one committed field element per 128 zeros. Whereas with the elliptic curve commitment schemes, I literally just pay no price at all in commit time for the zeros. And the price really only comes in with how big the commitment key is. So that's why you need to set D to be bigger. You need to set D to be bigger because we just really can't afford to have such giant committed, vectors with Binius or Blaze. But if you do set D to be like 16, you still come out ahead. In this case, k to the 1 over D would be like 2 to the 4th, which is like 16. And so, committing to one address with D equals 16 and K 2 to the 64 is it's D K to the 1 over D zeros, or like zeros and ones. And here I said K to the 1 over D was 16 and D is 16, and so that would be 256. And so this can be packed into two field elements. Right. So I can basically do, one lookup into a table with size 2 to the 64 by committing to only two field elements to specify the address. That's actually pretty good. That turns out to be much better than what would come out of existing lookup arguments, even if you use Binius or Blaze today. Okay, questions about that?
I wonder if there's chance or if there's sense to also explain how one-shot encoding is constrained if you would be willing to make the next session about this topic and twist because it's quite a lot to intake for one session.
Yeah, sounds good. Yeah, it's probably a good idea to just wrap up anyway. Yeah, that sounds good. I mean, I will say, it's mostly already captured by the hand wavy explanation I gave for why Shout only has prover time K plus T and not K times T. It's like, if I commit to T one-hot encodings, right? Those T one-hot encodings, you stick them all together and now you have a vector of length K times T, but there's only T ones. And so, the prover needs to, the claim that they're all valid one-hot encodings, like the first thing the prover needs to establish is that everything zeros or ones. Once it does that, then it wants to establish that in each row there's exactly one. Okay, and actually the most complicated and expensive thing by far is just making sure that everything committed is 0 or 1. Okay, and so Booleanity checking. Okay, and that's one big constraint system. The prover committed to K times T values. Okay, and there are now K times T constraints. So let's call the values, x1 to x K times T. And what are the K times T constraints? It's just that like xi squared minus xi equals 0, for I equals 1 up to K times T, right? Because this equation is only satisfied by 0 and 1 in any field. So it's almost the same situation as Shout itself. It's, we have a constraint system. It's huge, but the constraints are very simple. They're rank 1, and it's a very sparse constraint system because out of the k times t values, only t of them are non-zero. And so, you do the same kind of song and dance that I hand wave with Shout. It's a little different. Like we did have to write a separate, description of a prover algorithm. It's not literally the same prover algorithm, but, kind of you do the song and dance once and you get used to it. And, even when you have to change it a little, it's the same stuff going on. So it's the same, same thing here. Very, very big, but very sparse constraint system. And so we only wind up paying for the t non-zeros, basically. And in fact, we can even, this one is so nice and simple that like if k is 2 to the 64, we're not happy with k plus t, right? Because even the plus k term, even though it's not k times t, it's k is so big you're not even happy with k plus t. This is so structured that you don't even have to pay for linear and k in this case. So you can actually the runtime we can get is like k to the 1 over some c. I think it's this. It's like c times k to the 1 over c plus t. That I think is what we achieve. So even giant memories, k times t committed values, you don't even pay linear in k. You only pay linear in t. So just giant, sparse, structured constraint system all over again. Anyway, so I'm happy to elaborate on that next week if that would be valuable, or just talk about Twist. Either way, let me know if you have any follow-up questions to this, though.
Cool.
Thank you.
Nothing in chat.
Okay, well, thanks for letting me present Twist and Shout, or Shout anyway. Hope it was followable and valuable. So maybe we'll do a little bit of Shout next week, and after that probably Fry. So I'll figure out what exactly makes sense. So thanks again, and see you next week.
See ya. Bye, y'all.
Bye.